So hello everybody. Today we are taking up second part of the solid state. In the first part we have taken up the solids, its a type and the unit cell and what are the geometries possible and so on. In this part we will be talking about the closed packing in solids, how atoms are packed in solids, and then if there are spaces between the atoms or molecules in the solid arrangement, what kind of voids or spaces are there available and the nature of them, geometry of them, then determination of the formula of compound based on the occupation of ions, especially in ionic solids, and then packing efficiency in solid. Are they 100% efficient in the packing? And how much space is present? So in terms of the mathematical expression will derive, and then calculation of the density of the solid and so on. Right. So what is meant by close packing in solids? Close packing is the arrangement of constituent particles in the solid. Arrangement of constituent particles as we believe that there is least space between the particles of the solid. So if the solids are close packed, that means they leave minimum space between them. So if suppose the atoms or molecules are arranged in one dimension, how they could be? So we understand about this pattern in terms of 1, 2 and 3 dimensions. So if it is one dimension, the how it looks like, and also the coordination number associated with the kind of arrangement. This is what we are going to see that. So probably you must have seen the vegetable like tomato arranged in this way, right? This is one way of stacking of solids, keeping one over the other, stacking of solids. So this is the three-dimensional arrangement, right? To understand the three-dimensional arrangement, we will take up the arrangement in different dimension. Okay, close packing in one dimension, so it looks like this. The atoms are arranged in this way so that they touch each other. This is the only one possible way when we arrange the particles in a row. Since each particle is in touch with the two, it is said to have coordination number 2. So coordination number is the number of particles that in touch with the given particle. So that is coordination number. So in one dimension, the coordination number is 2. Suppose if the atoms are to be arranged in a layer, we call it as two-dimensional arrangement. So the atoms can be arranged in this way in one row. The second row may be just similar to that of first row. So this is also called A kind of arrangement. Here we mean the A rows are similar in the arrangement. And in this case, each atom will be in contact with or in touch with the 4. Therefore, this coordination number is 4. So is it the only one way available for the two-dimensional arrangement? No. There is another way as arrangement also is possible. Suppose if you keep one row here A, so little bit B outside of it, so that this depression of the second layer will fall on the A here. That means this is another kind of arrangement. So here rows are not at the same place but at the depressions. So there are two possibilities. One is A kind of arrangement, another is A B kind of arrangement. Now here if you see, each atom is in touch with 6 other atoms in the arrangement. Therefore coordination number is 6. And this is considered to be more closely packed than this. So this particular arrangement, that is A type of two-dimensional arrangement, is called square packing. Square packing. And this arrangement is called hexagonal close packing. Hexagonal close packing in 2 dimension particularly. Now look at the third 3-dimensional arrangement. Okay, so the arrangement of 3 dimension should be made such a way that over the one layer, another layer is to be arranged. So over one layer there should be second layer. When second layer is placed in the depression of first layer, then there are 2 voids are being formed. Voids mean spaces. Now you can look at the diagram here. So one dark circles are there, that is the layer above the one which is under it. So this is faded circles indicate the lower layer. Now you can see that each atom in the lower layer, here it is surrounded by 3 above it, 3 above the upper layer. So such kind of voids are called as tetrahedral voids, and these are named as T here. Now there is another kind of void also is being formed. The 3 in the first layer, this is a faded circles you can see, 3 in the one layer is surrounded by the 3 above it. The 3 above it. Okay, so here 3 above it, 1, 2 and 3. So 3 below layers are being closed by the 3 above, and such kind of voids are octahedral voids. Let us take the clear picture of tetrahedral voids and octahedral voids in this slide. So the vacant space surrounded by the spheres in the solids are called as voids, and they are called tetrahedral and octahedral voids. And how these exactly are? So here the color is being changed. So 3 in one layer, that is green circles, and above which one is closing the space between that is tetrahedral void. So exactly this way it looks. 3 in one layer is being closed, this space is being closed. So this is tetrahedral void. And if 3 in one layer, below layer, is closed by the 3 above, 3 in one layer closed by the 3 above, placing it in different way, so this will give octahedral void. So these structures based on the geometry, they are all being named. Now coming to how many voids will be there in the arrangement. Suppose in a closed packed spheres, if there are n number of spheres are there will be totally tetrahedral voids will be 2n. In closed packed structure, if number of tetrahedral voids will be double of number of sphere by which it is being made, and number of octahedral voids will be n. So remember that there will be totally 3n number of voids when there are n number of atoms are there in the close packed arrangement. Now we will have a question of this type will be asked in the examination. Atoms of an element B forms HCP structure, HCP lattice, and those of the element A occupy 2/3 of the tetrahedral voids. What is the formula of the compound by the elements A and B? So here A and B are the 2 elements by which it is made up of. Now B forms HCP. So let there be hexagonal close packed structure. Hexagonal close packed structure, let there be n number of atoms. So we will take it like this. B is n. Then A is occupying 2/3 of the tetrahedral voids. So this will be 2/3 of tetrahedral voids. As you know that if there are n number of arrangements in the n number of arrangements then of atoms, then there will be 2n number of tetrahedral voids. So number of A will be 2/3 of 2n. So you keep it in the simplest way so that n can be cancelled. So this is 4/3 and 1. or you can say A4B3 is the formula of that compound. So this is the way we can able to solve. So let us visualize voids in solids. So there are octahedral and tetrahedral voids.
The face-centered cubic lattice contains 8 atoms at the 8 corners of a cube.
See, it is an arrangement to be looked in different angles. The one which is at the corners and at the centers of the space are being named as green. You can see that here 3 atoms are being closed by one above. So each corner, the atom at the corner closes the gap between the 3 which are at 3 different faces. So below this there will be a tetrahedral void. There will be tetrahedral void. So that will be the location of a tetrahedral void in case of FCC. This is an FCC arrangement. Now in order to look at it by layer, we will find that how layer by layer they are get arranged. Right? So this is an octahedral void. 3 atoms is being closed by the 3 below it. Okay, so 3 you can see, or else you can look at it in this way: 4 atoms in one layer being closed above and below by the 2 particles, that also called octahedral void. So octahedral void can be seen in 2 different ways. 3 in one layer closed by the 3 above, that is the one way. Another way, if you look at it, 4 in one layer being closed by 1 above and 1 below. So that these are all the position of octahedral void. Octahedral void, one totally will be there at the center and other octahedral void will be there at the center of edges. Each center of an edge, that will be the center of an octahedral void. Now look at the particle arrangement layer by layer. So, if there are n number of atoms, there will be 2n number of tetrahedral voids. This can be very well tested by counting the number of tetrahedral voids. Totally in FCC, there will be 4 atoms. And below each corner, there will be a tetrahedral void. That means how many corners are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 corners are there. Therefore, below that or inside the unit cell, there will be 1 each. Therefore, if the 4 atoms are there in FCC, 8 will be number of tetrahedral voids. So, that is the place. And here is the place of octahedral void. So, that will be at the center of the edge. Yes. So, one whole thing is there at the center. And at each edge there will be a octahedral void. Now can you tell me how many unit cells each edge will share? each edge of one unit cell is shared between how many unit cells? It is 4, right? 4 unit cells are being shared. That means one space at the center of the edge is being shared by 4. That means one fourth of the octahedral void, is there at the center. 1/4 is there at the center, right? So how many edges are there? 12 edges are there. So 1/4 of 12. So 1/4 of 12 is 3, and one hole inside the cell, inside the unit cell. Therefore, there are 4 octahedral voids. So there are 4 particles in FCC and 4 octahedral voids are there. That means if there are n number of particles, n number of octahedral voids will be there. So this is the way we have to understand about it. Then we'll take up the close packing in the 3 dimensions. That is how the arrangements are possible when the layer by layer it is to be arranged. 3D close packing from 2D close packing layers we have to have. There are different types of 2D close packing is possible. 2-dimensional close packing is possible. Now A type and another is AB type. By using this layer, there are different ways the total arrangement or 3-dimensionally arrangement can be made. Now, the lattice generated by simple cubic lattice. Simple cubic lattice is by this way. Now look at this. This is AA type of layer. AA type of layer. So that kind of layer is arranged one over the other. 3-dimensionally will generate a unit cell which is primitive. You can look at the unit cell which is primitive. So only at the corners particles are there. So this kind of unit cell is due to the arrangement of AA 2-dimensional type of layers to form 3-dimensional AA type. AA type. So this is A layer, this is A layer, this is A layer, and so on. They are placed one over the other similarly. Now, what is the another possibility? So if you take the layer which is AB type, this is the AB type, a small piece of that is being taken. So if you keep the 3 atoms just over that, so that you will get the depression at these points, depressions over the first layer. For first A depression of this, it is being taken, and in this depression, this is being taken. In this way, if 3-dimensional arrangement is being made, right? So this is called AB type of formation. AB type of formation, and for such kind of arrangement, coordination number will be 12. And this is called hexagonal close packing, called HCP. Hexagonal close packing. This will be the pattern of a unit cell. Here is a pattern of a unit cell, and this is the hexagonal close packed structure, and unit cell will be hexagonal geometry. It will be having hexagonal geometry. Now there is one more arrangement possible in a 3D packing by using 2D hexagonal close packed layer. So here the arrangement is ABC type. A layer, the depressions, there are 6 depressions you can see. 1, 2, 3, 4, 5, 6 depressions are there. 3 depressions are covered by this layer, and the 3 other are covered by the next layer. So that is C layer. C layer, B layer are different. Now A, B, C, again the same kind of layer is there. Therefore ABC kind of arrangement is called as cubic close packed structure, cubic close pack, or simply CCP. And here also coordination number is 12. Coordination number is 12, right? So this is cubic. Now we will visualize the close packing in solids. So solids have long range order, and you can see the atoms are being packed So as I told you, the two dimension, this is square packing and this is hexagonal close packing, two dimensionally when you speak. When you keep one over the other in the similar way, for the 2D pack you get square packing. This is square packing. Such layers are being taken, kept one over the other in the similar way, that means A type. So this will lead to a unit cell which is of primitive type. Unit cell will be of primitive type. This is called A type of packing. Okay, so each unit cell looks like this, right? This is a space filling model, and this is written so that you can able to see the unit cell pattern. So this is cubic one. Now two-dimensionally you can choose either this one or this kind of layer, right? So suppose if you take HCP layer is being formed in AB way. Taking this layer, if you arrange, okay, so if you, these are the voids there, the one which is shown as red one. By taking such layer, you keep one over the other in such a way that this is being filling the spaces or voids. Okay, so that this is the second layer, and the third layer similar to that of first layer. If third layer is similar to that of first layer, then it is AB type. Right? See the voids, where the voids, octahedral voids are there and tetrahedral voids are there. You can have a clear picture in this regard. Okay. Right? So the unit cell was primitive type earlier. Now okay, there is one more possibility. Taking hexagonal close packed layer, that means 2D hexagonal close packed layer, keeping one over the other in ABC form. In ABC form will lead to, so this is A and this is B layer, right? Partially the voids are being closed. All voids cannot be closed. Now the third layer is to be placed. If this layer is being placed, third layer is being placed, not similar to that of A layer, but closing the voids which are not being closed by the second layer. That will lead to cubic close packing, and it generates a unit cell which is called FCC, right? Iron, copper, silver. So you can look at the structure of that is CCP. Iron, copper, silver form CCP. So here distinguish between these two, right? In HCP, A, B, A. They are same. A, B, A. This layer and this layer are same. These pattern of arrangement is same. But here, this layer and this layer are different. You can visualize the placement of these atoms. So HCP and CCP, even though they look same, but they are different when you look at each unit cell. In HCP, hexagonal close packing, this is the one unit cell. This is the model of one unit cell, that is FCC, face centered cubic, when the arrangement is cubic close packing. So this is how you can distinguish the different kinds of arrangements and generated solids. Right? Now, how to determine the formula of the compound? Let us take some more questions on this. A cubic solid is made up of two elements, X and Y. Atoms Y are at the corners of the cube and X at the body center. What is the formula of the compound? So this is a question in which the arrangement is cubic. Arrangement is cubic. And element Y are at the corners. These are all Y. These atoms are Y. And X at the body center. This is X. And these are all Y. These are all Y. But these atoms or molecules which are at corners do not belong completely to the unit cell. The formula is not XY8. This is wrong. It is because the Y completely, one atom is here, doesn't belong completely to the unit cell. So only 1/8 of this particle is inside the unit cell. So to determine the formula, we always have to take the number of atoms inside the unit cell. So 1/8 of 8 are there. Why 1/8 of 8 are there? So that X 1/8 of 8 Y are there and X completely 1 is there. So X1 and Y1. It is the formula of the compound. Formula of that compound. Okay, based on the arrangement and the placement, you can able to determine the formula of the compound. So for that, you should have the correct idea about how they are arranged. A cubic solid is made up of two elements X and Y. Atoms Y, anions, are at the corners of the cube and X atom present at the face center of the cube. What is the formula of the compound? So there are two elements. Anions are at the corners. Anions are at the corners and cation is present at the face center. So the one which is at the corner, 1/8 of 8 belongs to the unit cell, that is 1, and those which are at the face center, there are 6 faces are there. So half of that only belongs to the unit cell. Therefore, 1/2 of 6, that is 3, belongs to the unit cell. So that number of X per unit cell is half of 6, that is 3. Number of Y is 1/8 of 8, that is 1. Therefore, the formula is X3Y. So, understand the sentences clearly and then determine the formula of it. Now let us see what is the relationship between the edge length and the radius of the atom. So in the arrangement, we can able to find out the relationship between radius r and edge length. So here is the unit cell and these are the atoms. So these are the adjacent atoms. Now you can see the distance between these centers itself will be the edge length. Now, so if the radius is r plus r is equal to edge length. Therefore, r is equal A is equal to edge length is equal to 2r. Now suppose if you take another arrangement, that is FCC. In FCC, the atoms along with the diagonal of a face they are touching. So this is at the corner, this is at the corner, and it is at the face center. Face center. So these atoms are in one line. Therefore, R plus R plus R plus R. 4R is equal to face diagonal. Face diagonal is given by root 2A. Root 2A, this is edge length is A, then if the edge length is A, this is root 2A. Diagonal is given by root 2A. Root 2A is equal to 4R. Therefore, A is equal to 4R by root 2, or you can be written as 2 root 2R. Now, coming to the BCC. In case of BCC, the spheres which are touching is opposite. This is a body diagonal. It is body diagonal. Okay. So, body diagonal is given by root 3A. So, root 3A is equal to R plus R plus R plus R, 4R. That means A is equal to 4R by root 3. So, this is the relationship between edge length A and R to be remembered. Now, let us see the close or packing efficiency. Packing efficiency is the fraction of total volume being occupied. The fraction of total volume of the crystal being occupied is solid 60% filled, 70% filled. In this way, we can able to talk in the terms of percentage also. Packing efficiency can be expressed in percentage also. Packing efficiency, the formula can be written as volume of an atom per unit cell divided by volume of the unit cell. Okay, volume of atoms, all the atoms per unit cell divided by volume of the unit cell. So volume of all the atoms can be given by number of atoms per unit cell into volume of one atom, volume of one atom. So volume of one atom into number of atoms will give you volume of total number of atoms. So here we can derive, this is number of atoms per unit cell is taken as n here, and volume of one atom, as we consider this as a sphere, this is 4 by 3 pi r cube, and volume of a unit cell, since it is a cube, a cube. So a cube is the volume, A is edge length, therefore a cube is volume, R is the radius of the atom, and n is number of atoms per unit cell that differ for different kinds of cells, different kinds of cell. Right? So we will take up different kinds of cells, that is simple cubic, BCC and FCC. So packing efficiency is, if it is expressed in percentage, then it is to be multiplied by 100. Volume of one atom into number of atoms divided by volume of the unit cell. Since it is simple cubic, number of atoms is 1. Number of atoms is 1. So this is 4 by 3 pi r cube into 1 divided by, so 2r. R, what is the edge length? A is here 2r. Therefore 2r whole cube is nothing but 8r cube into 100. If you simplify this by taking pi is 22 by 7, we get 52.4%. That means the simple cubic arrangement, simple cubic cell is 52.4% efficient. Now, coming to the packing efficiency of face centered unit cell. Same formula, volume occupied by the spheres in the unit cell into 100 divided by total number of total volume of the unit cell. So, volume of the unit cell A is 2 into root 2r whole cube. In the face center, the cubic unit cell, there are 4 atoms. Number of atoms is 4 into 4 by 3 pi r cube into 100 will give you in percentage. So if you simplify it, it is 74%. 74%. See the difference. So here it is 74%. It is only 52.4%. So this FCC is more closely packed. FCC or CCP, cubic close packed arrangement, is more efficient in the packing. Now coming to the body centered unit cell. In the body centered unit cell, 2 number of atoms are there. 2 atoms into 4 by 3 pi r cube into 100 in the numerator, and edge length in terms of r is 4 by root 3 into r whole cube. Again, by simplification we get 68%. So body centered cubic unit cell is more efficient in packing than simple cubic or primitive unit cell, but it is less packed compared to FCC, right? So in comparing packing efficiencies, so you can comprehend this. Simple cubic 52.4, BCC 68%, FCC 74%. So 100 minus this will give you white space. There are almost equal space, white space is there in this arrangement, right? So this is close, FCC is closely packed because less white space is present. Now, can we able to determine density of the unit cell based on the measurement of a unit cell? From unit cell dimension, can we able to measure? Yes, we can able to. So as we know that the density is given by mass of the unit cell divided by volume of a unit cell. Mass by volume is density. Mass of a unit cell by volume of a unit cell will give density. Now mass of one unit cell is given by the mass of all the atoms present in a unit cell. So there are n number of atoms, or Z is symbol which is being used for writing number of atoms. Number of atoms into mass of one atom will give you total mass of all the atoms. So this is mass of atoms in the unit cell. A cube is the volume of the unit cell if A is the H. Now this mass per unit cell can be determined if you know the molar mass and Avogadro number. So if molar mass divided by Avogadro number will give you the mass of the substance that is being taken. So from the cell dimensions and molar mass you can able to find out the edge length, or you can able to find out density of the unit cell, right? So what we have talked so far is about the closed packing in 1, 2, 3 dimension and in solids, and tetrahedral and octahedral voids, formulation of the compound, how the formula of the compound can be determined, especially in ionic solids, and packing efficiency of different kinds of arrangement of unit cell and calculation of density of the unit cell, right? So a few questions to note here. They are: calculate the packing efficiency in case of a metal crystal for a body center cubic. So derive this can be asked. Derive, or you can derive the formula and also you can substitute and find out how much percentage, that is 68%, you will get the answer to that. Now, niobium crystallizes in body center cubic structure if the density is 8.55 gram per centimeter cube. Calculate the atomic radius of the niobium using its atomic mass 93U. So this is based on the formula that rho is equal to Z into molar mass divided by Avogadro number into A cube. A cube where A is the edge length. Okay. So this by finding out edge length, and we can able to find out the radius also. Keep on trying, and thank you.